I tried to open the shades, but they just closed again.
Thank you for trying. I appreciate it.
Well, I like the sun. Yeah. All right, let's get started. This is part 2 of our algorithmic approach, our computational approach to finding Lyapunov functions, right? Gone are the days where we have to be creative and cancel terms. Well, not completely, but you know, we're going to do pretty well with the algorithms that we talked about last time, which we're going to extend into the domain of nonlinear functions, nonlinear dynamics this time. Right? So last time we introduced a few ideas that we're going to build on today. So we said if we are given a closed-loop dynamical system, no U here, this is already with the feedback looped in, then we're going to formulate the search for Lyapunov functions as an optimization problem. And the key idea there is that we're going to parameterize v of x as oftentimes, always for this week, a linear combination of nonlinear basis functions. And then we're going to try to search for alpha, the coefficients alpha, by writing an optimization problem. It could be a feasibility problem, or it could be, we could maybe try to optimize some objective, but at least we'd like to find some alpha subject to the constraints that for all x not equal to 0, let's say v of x is strictly greater than 0, p0 equals 0. These are the conditions that you know and love, right? Okay, but we haven't turned this general formulation into an algorithm yet, because that for all x is a hard thing to do in general. So we had 2 initial algorithms last time, right? The first algorithm, we said we know how to sample a bunch of points xi, and we could say for all I, you know, this is some finite set of samples, right? And then we could say for all I and enumerate those, we have these properties hold. That was really nice for a number of reasons, because first of all, once I insert x into these things, everything that was nonlinear just becomes a number, right? And so we're left with something that's just you know, a bunch of numbers multiplied in a linear way by alpha. So the result of that was a linear program. For which we have, you know, that's a convex optimization problem. It's got constraints, but we have really good solvers for solving linear programs, and they scale really well. But that analysis is only ever going to be restricted to those sample points, unless you do a lot of work to say something about the regularity conditions. You could try to grow it, but it's not a certificate of the true for all x. And sampling in general scales badly into high dimensions. So we started our progress in the quest for all x with looking at linear systems, right? And in linear systems, we were able to choose quadratic Lyapunov functions, which I hope you realize is just this. That's just a version of this. Because the elements of P, if I were to expand this out, call it alpha 1, 1, alpha 1, 2. If I multiply that through, that's going to be alpha 1, 1 times x1 squared plus alpha, right? It's good. It has nonlinear terms here, but it's linear in the coefficients. So that is just an example of this form. It's a little hidden, okay? V dot in that case was x transpose P AX plus x transpose A transpose PX, which we could also write as so our conditions became, our Lyapunov conditions for all x could suddenly be summarized by just saying that if P is greater than 0, is positive definite, and PA plus ATP was negative definite, then we can say something for all x, right? And this turns out to be something that we can do with the tool of semi-definite programming. Which is still a convex optimization, still good tools, not quite as mature. They are fundamentally numerically harder, more squirrely than linear programs. So they won't scale to as high dimensions, but you don't have to, this one, in order to do a good job, I might have to sample thousands of x points. Here, P is 2 by 2, for instance, in that example.
So the thing that we can say about x is that it is stable if we can find a set of alphas that satisfy those, right?
Correct. In this case, alphas are what populates P. Correct.
Thanks.
Yep, and the conditions you have to check now, x is gone.
Yeah.
You just have to check the positive definite, the eigenvalues effectively of these matrices. Yeah.
But also, so it looks like the second method is constrained to linear systems.
So far, yes.
Whereas the first method could be whatever you want.
Exactly. Yep. True. So today is how do we take the second method and grow it towards nonlinear systems. And the idea is, okay, I'm going to write it in a way that makes it sound simple, and then we're going to realize it's not quite that simple. But all right, really simple here. Okay, let's just go from v of x, like that, to let's just do this. Oops, don't need that one. All right, I could take any function. I've been calling it phi before, but just because it's a little bit different, let me use m, and there's a good reason to use m later. Okay. But certainly, if p is positive definite here, then this is also true for all x, right? This is also greater than or equal to 0 for all x. Yeah? I hope we convinced you of that last time, if it's not visually obvious. All right, so that's the trick. That's it, right? But we have to do a little bit more work, right? Because once I start doing this, I have partial m partial x times f of x. Right. This is for the now nonlinear case. Okay. Plus the opposite of that. Right. So the same thing on the opposite side, just like I did this symmetric part. Okay. And unfortunately, this one is not, even if this is a simple matrix condition, this one doesn't have some obvious symmetric form, right? It has some, whatever f gave you on the other side, So it's not by inspection sort of obviously a symmetric thing with some middle condition that we just have to check for positive definiteness. Okay? So how do we get to this? And the trick is, it's actually very similar. Remember we talked about how, okay, we know how to do p greater than 0. That actually means we can also do this. By the trick, we can extend it from semi-definite matrices to linear matrix inequalities, because I could always write this or sorry, less than 0 in this case, right? And then the constraints, I could say that basically all of the elements of this have to equal, right? So I say Q11 has to be equal to whatever P times A11, right? This equality constraint is just a bunch of linear constraints in A, and then I could just make that new variable and do it like this, right? So if I know how to put constraints on the positive definiteness of matrices and optimize over the set of positive definite matrices, then I can also do this. I'm going to try the same trick here, okay? So we're going to say this thing, I'd like that to make that equal to, it's going to be a different m in general. So that's a different basis potentially, okay? But if I can find some different basis where the linear, where every term of this, equates, then I can actually say that this thing is positive. And in fact, the decomposition that we're having here is called a sum of squares decomposition. So you should ask yourself, that seems too good to be true, that I take arbitrary nonlinear functions and I can write them in this form with just linear constraints relating them. And that is too good to be true in general, but there's an important big class of systems for which actually that works really well. In particular, if M is polynomial, if this whole thing is polynomial, then we know a lot about how to construct these m hats. For instance, if I have 1 plus 2x plus 4x squared or whatever, then I'm going to guess m is going to be 1 over x transpose q 1 over x, for instance. I could take the degree of the polynomial, divide it by 2. I'm never going to need more than half the degree because I'm going to square them, and I could list out all of the possible, by writing it a basis like this, I can get all possible elements. I picked a very bad one here, right? So that one is obviously positive. Well, I guess the one I actually thought about was 4x plus 5x squared, right? So if you were to just look at this and ask, is that positive for all x? I think you could work it out without too much trouble. You would maybe take the minimum over x, because you know this is positive. You could figure it out. But I can also convince you of it really quickly by doing a sum of squares decomposition, right? If I just write it instead like this, that's just another way to write that. And now it's obviously positive. And that's effectively what's happening by finding a Q that's positive definite, that's a linear combination of these basis functions, okay, it's effectively factoring this into a sum of squares decomposition. So, right, to see that, so, and just to understand that this would be linear equalities, right? So I would have this constraint. I'm going to make new decision variables for the matrix Q, which is a 2 by 2 matrix. And then I have Q11 has to equal 2, right? That's a constraint. I have all of the quadratic terms. I'll pick this to be symmetric too, by the way. Like there's Q22 is going to have something to the power 2, x squared. So that one had better equal 5, right? And I can list out, for each of these, the elements of this have to satisfy, right? Q12 plus Q21 are going to be the coefficients of x, and that had better equal -4. You see how those are going to just give linear constraints plus a semi-definite constraint. So certainly, if I take a polynomial, if I write this out, and I can find a positive definite Q, which satisfies all the equality constraints, and is positive definite, right? Then that is a proof that this thing is a positive definite function, that it's greater than 0, except at 0, yeah? There is a chance, so the other question is, can I always find a factorization of this form for every polynomial? And the answer is actually no, in general, but we're going to ignore that in this class, most basically. So, well, for univariate polynomials, I think it's tight, and for low degree polynomials, there's a few special cases where it is tight. But in general, if I have polynomials of many variables, there's not actually a guarantee that I can always find sums of squares decomposition, but you normally can. In fact, when I was saying last time, you guys were asking if you use optimization, how you use optimization in duals. People have used optimization in order to try to find counterexamples of polynomials that are actually positive, but cannot be proven positive with this. And there's some famous named polynomials, the Motzkin polynomial and stuff like this, that are the counterexamples. So, you have to look pretty hard. You get a paper written if you find a counterexample that has like whole value, whole number coefficients and stuff like that. That's like awesome, rational coefficients. Okay, so in practice, we're going to say that we do have a tool now for checking positivity of polynomials with this idea. Okay? That's a big deal. So our modeling power just went way, way up, right? So a few minutes ago, we were pretty happy to have linear objectives, linear constraints. We took a huge step when we said we can do linear objectives, but suddenly add symmetric, positive definite matrix constraints. And now we're saying that we actually have the modeling power to say, minimize, for instance, some coefficient, some linear objective over alpha of p of x under the condition that p of x is greater than or equal to 0, where p of x is alpha 1 plus alpha 2 x. It's any polynomial with the alphas as the coefficients. Now, because there is a gap, and I don't know that I can do this exactly, I'm going to write this more correctly by saying is a sum of squares polynomial. SOS. There's Pablo Perillo, who's the one who sort of popularized a lot of this, especially in control. He likes to make jokes about the Titanic and stuff, but somehow he ended up calling SOS, and it's a big part of his contribution to the world. So, all right, so suddenly we can formulate problems of this form. Our modeling power just went way, way up, and and saying this is a convex optimization problem. Okay, and this is called sums of squares optimization. And like semi-definite, like linear matrix inequalities, when if I were to write a problem like this, in order to hand it to a solver, I have to, on the back end, make some new decision variables, make some equality constraints, some positive definiteness constraints, right? So there's a bunch of things that happen, but then I could then hand it to a semi-definite programming solver. In practice, there's a few front ends, of which we have one in PyDrake, or Drake, that do this for you, that make it so you can really write things of this form. You can just say, I have a polynomial, I'd like it to be sums of squares, you add it, and it takes care of the details in the back end. Okay? That took a lot of effort, so I hope you appreciate it. It's really good. So Frank Permenter in particular was a student that was working on some of the pre-processing algorithms that go into this. I should say that sums of squares polynomial, this constraint, just like semi-definite programs turned out to be harder than linear programs in squirmy ways. Like you can write a perfectly good STP, but the solver might say it's having numerical troubles. That happens even more often with sums of squares. The way you would, the standard transcription to sums of squares problems often causes the solver to complain about numerical issues. Frank is a student that was here that did a lot of really nice work on cleaning that up. And I think in practice, roboticists who had played with sums of squares before gave up on it because of numerical issues, and we've sort of fought through the numerical issues enough that it works pretty well. Okay, so when I first saw this, it was one of those, because if you think about the modeling power of this, it allows you to do things that you shouldn't be able to do. Okay, let me try to give you an example. There's a famous function called the six-hump camel. Okay, the six-hump camel. It's a famous and, well, I guess in sort of nerdy circles maybe only, but you don't have to write that down, obviously it's in the notes, but okay, it's just a fairly benign looking polynomial equation in two variables. So I should be able to plot it, right? It has terms up to the sixth degree 6. And I'm going to plot it for you here. Python six-hump camel. All right, this is what it looks like. Did I write something not big enough or something?
You have a 4x squared, and then you have a minus 4x squared, right?
Yeah, I do. And here too, but not in the code, presumably. Yeah, I'll fix that. But let me see, what did I type in? Yeah, that second one's a y.
Cool.
Yeah, that makes a lot more sense. Let's make that a y. So what do you get when you plot that function? You get this nasty looking thing, okay? So that is, the reason it's famous in small circles is that it's a good problem for testing nonlinear optimization, right? So I drew some of the, I was like, it's actually sort of hard to come up with a nice function that has just a handful of local minima. They're all sort of understandable, all kind of near the origin, but clearly there's a bunch of local minima here. There's 6 of them, in fact. 2 of them turn out to be equally good global optima. Okay, 6-hump camel. All right, and this is just the contour plot of the same thing. So should be like finding the minimum of that should be a hard problem, right? Of course, harder in high dimensions. I could just check enough times on this, but how do I write an optimization that finds that? It turns out sums of squares. This formulation is a convex optimization problem that can find the minimum of that function. Right? So how do you do that? I'm going to say I'd like p of x minus, let's say, p min, or I call it lambda, okay, is a sum of squares. This is equivalent to me, almost equivalent to saying p of x is greater than lambda. Right? And then I'm going to say maximize lambda. This is for all x, p of x is greater than lambda. Maximize x. Okay? And the code, which had the correct letters, it's 3 lines, right? It's really small there, but I'll make it bigger in a second here, just to make sure you see it's 3 lines. Okay, and what does it do here? It calls a semi-definite programming solver. I had printing out some information, and it finds a lower bound. It's not. So this is going to do its best up to the limits of being sums of squares, because there is a small gap here. But it's going to do its best to find the biggest lambda, which is a lower bound of that function. Okay, and it's ridiculously tight. Okay, the minimum value I was able to sample, well, I didn't. I sampled pretty coarsely, just whatever showed up on that mesh. Okay, and the sums of squares optimization, a convex optimization problem, found that minimum value effectively. Right? I like it's tighter. If I were to just sample more finely, it would be even tighter than that. It's effectively found the optimal solution. Right? That's cool. It's weird. Like it should be. That seems like that should be a hard problem, but somehow casting it like this is a change of coordinates. It's a different formulation that has made that thing that looks very non-convex in 2 dimensions into something we can optimize globally with a convex solver. Cool? All right. So naturally, we're going to use that same idea to do Lyapunov analysis. Okay. There's one caveat. I found a lower bound of the function. I didn't actually find the x that minimized the function. So if you need that, you have to do extra work. You actually can do extra work with the dual of the optimization problem, and you can zoom in, and there's a package that does that, and I put a link in the notes for it. But we don't need that for Lyapunov, and things work best if you don't need that, maybe. But being able to prove that something is greater than 0 or less than 0 is what we need for Lyapunov, and we have that, right here. Okay. All right. So this is a new modeling power that we have that is, I think, you can see, is pretty close to what we want for Lyapunov analysis. In particular, let's say I have x dot of x is p of x, so polynomial function, right? So f in general could be anything nonlinear. Let's restrict it to just polynomial vector fields. I'll try to convince you as we go on that actually most interesting things are polynomial or close to polynomial. Okay. All right, and let's say that I have v of x. Let's choose that to be a polynomial too, okay? Also polynomial. How do I want to write that? I didn't choose my variables very well. I'll just call it v of x is also polynomial. Then v dot of x is, we know it's partial v partial x transpose p of x. One of the nice things about polynomials is if I take partials with respect to x, this is still polynomial. And it's closed under multiplication too. So this whole thing is also polynomial. Okay. So I can actually, write optimization problems in a few lines that say search for a v of x, or even the simplest case is just to verify. Let's say you have a Lyapunov function. You come to the table. You say, I think this is a Lyapunov function for this system. A reasonable test would say, find me my hidden variables q, such that my v of x polynomial is sums of squares, and negative v dot of x is sums of squares. Okay. Here's a polynomial vector field that we can show to be globally stable, that I can write on the board fairly quickly. Turns out we actually know, let me give the simplest version of it first. It turns out that this is a valid Lyapunov function. The way we found this actually was by calling sums of squares and making it find it for us. But let's say we're going to leap ahead and say someone just guessed that. Okay? So the first step would be just to verify a Lyapunov function. In this case, that one is by inspection positive. So the work to do is to write this v dot of x, which is what it's 2x1 1 minus x minus 2x2 squared, right? It's just works that out, 4x2 minus x. Now, I don't want to underestimate anybody's ability to do algebraic manipulations, but manipulating that around into some sums of squares, some obviously positive, or in this case obviously negative decomposition is more algebra than I want to do. Okay? So even just, we can use this tool, the sums of squares optimization, just to verify, right? I've got a v. I'd like to see, is this a valid Lyapunov function for that? That's sort of step one. And that entire problem is written right here, okay? You make a mathematical program. We're going to call x our indeterminants. They're the ones that we want our properties to hold for all x, but they are not decision variables. There's two different ideas that the solver has to understand. This idea of indeterminants, okay? My vector field, I just write f. My Lyapunov candidate v is just what I wrote here on the board. I can figure out v dot is just by taking the derivative, the partial derivative, and multiply it by f. Okay? I do a little bit better. I'd like v dot to be, strictly less than 0. Okay, so I put that little epsilon term in there, just to say that it's actually going down. And you call solver and it's done. And now this is a convex optimization. So if that was a valid Lyapunov function, it returns success. If it was not, it returns fail. It's nothing, it's not like, maybe. In the world we've got, sorry, that's not completely true. It returns success, fail, or I had numerical issues. And that's the one that can be annoying. But completely different than non-convex optimization where failure doesn't mean anything. This one, failure is a certificate that it's not a Lyapunov function. Yes?
Sorry, what are the decision variables in that? If x is indeterminate.
Right. Really good question. Let me put it back to you guys. What are the decision variables in that problem? I didn't add any decision variables, it looks like, right? Why do I even have to solve anything? That method prog.add_SOS constraint is making new decision variables, q, right? Adding them to the program, adding the constraint that q is positive definite, adding equality constraints to make sure that it equals v dot, and those are the hidden decision variables that are being solved. And I could print those out if I wanted to. In fact, that method would return the decision variables in case you ever want them. Okay, so that's awesome. So we don't have to do math anymore, or we don't have to do algebra anymore. We can just type in this and then check true or false. That's already progress, okay? But even better, if I wasn't able to guess that, and in fact the way we get it in the first place is what I'd like to do instead is I'm going to say, v of x is 1 plus, it's alpha 0 plus alpha 1 x 1 plus alpha 2 x2 plus alpha 3 x1 x2 plus, and I'm just going to list off a bunch of them, okay? And a standard choice would be to have all of the monomials, have a polynomial up to some degree, and just have all of the elements in there with free coefficients. Okay, now the amazing thing here is I can actually optimize in my sums of squares optimization over these parameters alpha, because it adds the decision variables q. It adds linear constraints, but if those coefficients are free variables, that just turns into an alpha here. That's still a convex constraint. I can use these as decision variables and optimize subject to the constraint that v of x has to be greater than 0, v dot has to be less than 0. Now, within the space of functions that I've parameterized here, the solver's going to find a Lyapunov function for me if it exists. Right? I gave it a rich search space in this case, and it's going to try to find alphas. And if a Lyapunov function exists that can be proven with sums of squares, then it'll find it. Okay? So that's just the second version of this, and it's only a few more lines. We could have discovered the Lyapunov function automatically by just having c be some extra variables and writing down v in terms of c. Okay, there's a bunch of ways I could have written that, but I did it in a quadratic form so that I could just say that I'd like v to be positive by saying c is positive, Definite, okay. And then v dot. That's awesome. So we can find polynomial Lyapunov functions for us. Okay. So step 2 was searching for Lyapunov functions. At least searching for the coefficients. Cool. In fact, when you run those up, you might add a few more terms to get the scaling right, but most of those alphas turn out to be 0, and you get something simple that comes out. Okay? Yeah?
Just make sure I follow. So M transpose Pm is just the quadratic way to write C transpose alpha. M transpose Pm just ensures that C is positive. C transpose alpha doesn't necessarily ensure by notation that it's positive.
Correct. Exactly right. So I could have added a sums of squares constraint on V. If I had written it just as alpha, you know, C transpose, whatever, I could have added a sums of squares constraint on V. And that would have been fine too. But since I was free to pick the parameterization, I just did it what I know to be a little bit easier for the solver, even though all of these problems are super easy for the solver. Yeah? Okay. That's the biggest point. Now of the lecture, right? So far though, we've only done global stability. We've just gained an oracle that can answer really good questions for us. Is a polynomial greater than 0 for all x? Ironically now, the slightly trickier question is going to be, is that polynomial always greater than 0 for some region of x? Right? Not sample points, that was easy. Global is now easy, right? The intermediate one is I want to have some, for all x in some set. And that's going to be the way we're going to do region of attraction analysis. Because life doesn't give you globally stable systems, right? In general, you have to find the region for which it's valid. So that's the next idea. But let me just make sure that people get this idea. Roughly. I mean, the good part is the work of deciding the basis of making Q. Those details are all abstracted away from you. We have mature enough tools that you can just write things in that abstraction layer. Okay? I guess one other thing to say is we talked about the gap, right? So they're hard to find, but there are positive polynomials which are not sums of squares polynomials. So there is a gap. If I don't find a solution, it means that there is no sums of squares Lyapunov function that proves it. It doesn't necessarily mean there's no polynomial Lyapunov function that proves it. Second caveat, there are polynomial vector fields that are stable but cannot be proven to be stable with a polynomial Lyapunov function. I mean, there's really no reason why they'd have to be, and you have to look sort of hard for them. But I cited a paper in the notes it's like a one-page paper basically. It's great. It's like a conference paper. They probably had 8 pages or 6 pages plus a 2-page, for $250. And they wrote a 1.5-page paper. They just said, here's a polynomial, asymptotically stable, no polynomial Lyapunov function that can prove it. Done. Okay. So there is a gap there too, but that gap has not been notable in my experience. That in practice, we're able to find polynomial Lyapunov functions. And I think really it's leveraging the versatility of Lyapunov, right? The fact that there are many Lyapunov functions that can prove a system is stable. If a system is stable, you got a whole family of Lyapunov. You got v of x, 2 times v of x, there's all kinds of Lyapunov functions that would still be going downhill, right? So it's not that hard to find a polynomial Lyapunov function. You have to be creative to find something that's sort of too hard, too squirmy. It goes off to infinity too fast or whatever to be to have a polynomial Lyapunov function. Okay. So that's global analysis with sums of squares. Local analysis at a fixed point we just do with linearizations. We already had that. So now let's see if we can do regional analysis, meaning a region of attraction. What I'd like to do is say something like P of x is greater than 0 for all x that's in the set of, let's say, some constraints g of x less than or equal to 0. This is the capability that I'm going to need, right? I have, for all x, P of x greater than 0 via the SOS relaxation, but I don't yet have the ability to knock off x just over some set. You almost do. You just have to think like an optimization person. So if you have this amazing oracle, think of it as something in ancient Greece, right? I go to the oracle and I can say, is my polynomial greater than 0? And they say yes, or they say no. Okay, so you get to ask questions like that. Given you have that oracle, and you can only ask those questions, I guess they're always she, I don't know, were they always she? So she only answers questions of that form. Can you trick her into giving you an answer to this question? And you can, okay? So the trick is what you actually ask is this. Okay, let me make sure I get my signs right. But so whenever g of x is less than 0, so first of all, I'm going to ask for a polynomial that's positive everywhere to be lambda. Think of it like a Lagrange multiplier, but it's a generalization of Lagrange multipliers because it can be a function of x. Lagrange multipliers typically are a scalar. This one can be a whole polynomial. Right? All of these are going to be polynomials for this. All right. So lambda is always greater than 0. Find me a lambda always greater than 0. Okay. What this means is that whenever g of x is less than 0, this thing can only be hurting me. It can be making it harder for me to prove that p of x is greater than 0. Okay? Because this term would have to be less than 0 in the region of interest. So if I satisfy this, if I'm able to find this proof, then I've obtained that certificate. Okay? Furthermore, when this is not satisfied, when this is positive, when g of x is positive, this is able to contribute positive terms, making it easier for me to satisfy this equation. So if p of x was negative outside the region, this could actually help the total contribution, the total thing to be positive. Okay? So this is called the S procedure, or it's like a Lagrange multiplier. It's also called the S procedure. Or if you're really good, it's positive Nullenstats. S procedure, think of it as a Lagrange multiplier. So once again, we've given ourselves a little bit more gap. It's possible that, well, let me be a little careful, but if you pick a finite parameterization of this lambda, right? So this is, if you pick this to be lambda up to some degree for all polynomials up to degree 4, for instance. Then for that finite parameterization, there's no guarantee that if this holds, I can find a certificate like this. But often we can, if lambda high enough degree, okay? And since I'm able to optimize over parameters, if g of x is fixed, but lambda has, I can let the solver find the coefficients of lambda to find the certificate. So that was kind of a lot, but this is a key idea of turning the ability to ask that question into the ability to ask this question. This question then becomes a tool that we can use for regional stability analysis. So for instance, you remember my favorite example? We wanted, so we know that v of x equals x squared is a good choice for that. We were able to show before that this was satisfy the conditions inside that region. This was useful to prove the region of attraction of that inner fixed point to be inside -1 and 1. Okay. But could we have gotten that from sums of squares? Could we have found that coefficient, or even just verify it? Right. So if I just typed in vx squared and I did my dv dx business, it's a trivial thing, but it's going to give me this polynomial that is only going to be satisfied in this finite domain. So what I'm going to do is I'm going to pick a lambda of x, c0 plus c1 of x. I think in the example I picked it up to the 4th power, even though I'm sure that's more than you need. And then I said, find c subject to negative v dot of x minus lambda 1 minus v of x is sums of squares. Why did I do this? V was x squared. So actually, the region I care about is the place where x squared is less than 1. So that was a perfectly good description of G in this case. V is fixed in this example. The only decision variables I have are the coefficients of lambda. Just one second. Right? V dot is even fixed because x, there's no free coefficients here, nothing here. So this is also fixed. So this is linear in those decision variables. Those are the only decision variables apart from the ones that get introduced behind the scenes to make it sums of squares. And I can ask this, and it should say yes. Here are the Lagrange multipliers that prove it.
One there is the same way as one normalized. That's the level set that's determining the boundary.
Totally related. In this case, I actually just hard-coded it. And I've also hard-coded the region, so I just picked it to be 1. But if I was to search, if I were to put a free coefficient here, then absolutely the same trick. I could have the scaling be absorbed by that. Right? I could always, it's often the case that I'll choose the one sublevel set to be my threshold, and I'll just let the Lyapunov function go up or down to make that work. Yeah? Okay, so that works. You type that in. It's a few lines, and you run it, and it says, yes, And here are my Lagrange multipliers that prove it. Okay, so that's how you do region of attraction analysis. But there's a few caveats here. Well, first of all, the numerics start to matter. Okay, so I wrote here for to be clear that I'm just going to do a find C, and that's true. Any C that I find will prove this is stable, prove it's the region of attraction. But it's slightly better numerically. And for these simple problems, it doesn't matter. But as you get to bigger problems, it will matter. Slightly better to say like maximize over CA. Put an objective on it. Just say maximize A. That could be a scalar. Subject to this. Is less than, let's say, negative A x squared. Right? So find a V that goes down as fast as possible that proves it. It's just a little better to push it against. So if you let the numbers wander around by themselves and have lots of possible solutions, then they have a way of finding themselves into places where zeros, it's like 1e to the negative 19 or something like that, and you just don't want the solver to have to think about that. So you push down on it a little bit, saying I'd like it to be actually negative, and I'll make it as negative as you can to prove that. And that just makes it a little numerically better. Okay, so this is really good, but it did assume that I knew what V was already, and I even knew what the level set that I was looking for was already. Right? You have to be a little bit more clever again to be able to search for V. It's, there's a handful of different tricks like this, and the optimization tricks keep coming to the point where it's empty right now. But I decided I should really have an appendix at the end that's called Optimization Playbook, which just has all these little tricks listed out. And I actually have a draft of that, and I'll push it out. But there's just a bunch of little tricks that come up in optimization all the time. Boom, boom, boom. There's a bunch of them. This is more than a trick. This is like a principle, I guess. But little tricks about how to turn something that looks non-convex into something that is convex. I'll try to make a nice sort of cookbook of those. All right, so what happens if V suddenly has decision variables? Let's say alpha 1 here. Okay, then I have a decision variable here. It also shows up here. If I'm trying to search for lambda and alpha of this, I've lost. It's no longer a convex optimization. I have something that has bilinear. I have terms that look like, alpha times C plus a bunch of stuff. Okay, it's not linear in the decision variables anymore. So you have to do something else to make that work. Okay, and there's a bunch of things you can do. In the full glory of actually searching for this, the problem really is nonlinear, and you have to do some sort of bilinear optimization, which you can do, for instance, by guessing an initial alpha, fix that, search for C. Lock in C, search for alpha. Lock in alpha, search for C. That's one strategy that does accomplish this. Okay. But there's another intermediate step, which is, let's say that V is fixed, but what I want to search for is the level set. So I know V is fixed, and this happens, for instance, in the LQR example. So if I want to stabilize the LQR of the quadrotor, or figure out the region of attraction, then I actually have a valid Lyapunov function. I have a pretty good guess of V from LQR. LQR gave me this X transpose SX, right? So if I want to ask the question, so I know that's a valid Lyapunov function for small, local to the fixed point. And the question is, how big of a region can I prove that it's a valid Lyapunov function for the full nonlinear system? So there's this intermediate step where you're not searching over V, you're just searching over the level of V that I can prove something about. That still, let me erase this again here. That still, if I were to somehow search over this, in this formulation is a bilinear optimization. It happens to be that rho, this level set, will always be a scalar. Okay? So line search is really not that bad for this. Even in high dimensional systems, that's always a scalar. So you could pick a rho. It also has the property that rho being effectively 0 is always going to work. And I increase rho until I stop being able to prove it. I found my region of attraction. That is an algorithm that is implemented in the code that you can use and works well. Okay? So, sorry to set a bunch of things without writing them. In this case, we said, it is non-convex. You can do things like bilinear alternations, which is you fix one, solve for the other. Another interesting case here, case 2, have V of x, but find rho, my sublevel set, and my lambda of x. In this case, I actually can do a line search. I could do bilinear alternations again. I could also do line search on scalar rho. Yes?
For higher order polynomials, I can kind of see how there might be like disjoint regions of attraction. How would you deal with those?
The same way I showed you the global optimization result, which even though it looked like it was solving, it shouldn't be able to solve that non-convex problem, you can, the level sets of V need not be a convex set. Typically they are a connected set, but they don't have to actually be an ellipse or a box or anything. They can be funky shaped. I wish I have one that's like a nice star, obviously convex, where it works pretty well. If it's fully disconnected, you have to be much more careful because even in this case, remember we talked about a bit about this before we used computation at all, that the way you'd want to prove something over a region is you have to have V dot going less than 0 over a region that is an invariant set. So the reason this is a good choice for G of x is because that has the property that once you're inside the sublevel set of the Lyapunov function, you stay inside that sublevel set. So that argument gets more complicated if you were somehow to have disconnected sublevel sets. There's really, you lose the ability to say, I mean, the total invariant set could be, you could start talking about, but it's hard to think about those particular regions. So typically we don't go there. You probably could if you were careful. Do you guys want one more trick? There's like a cool trick, okay? Which is, there's a slightly different question. Do you understand that this question says, I want to be going downhill I want v dot to be less than 0 whenever v is less than rho. That's what I wrote there. Right? This is v dot x is less than 0 for all x in v of x less than rho. That's this formulation. That's the natural one. You want to say that the Lyapunov function is always going downhill whenever I'm inside of my invariant set. There's a different formulation, which, if you're clever, also proves regions of attraction, which is to say that I want v of x to be greater than rho for all x where v dot of x is going uphill. Okay? If I ever found a v dot of x that's going uphill, it better be outside my region. Now, there's one more thing you have to do here, which is to knock out the origin, because this thing does go to 0. And I think I can almost show you that in code as well as I could write it on the board. In fact, I have it probably up here. So my dynamics is negative x plus x cubed. Make my v is just x squared. Lambda is this. Now I'm going to say that v is going to be greater than rho whenever v dot is less than 0. Okay? But I'm going to make a little exception. I'm going to go ahead and multiply the whole thing by x squared so that there's a 0 at the origin. Okay? That just, there's one case where that breaks, is that v dot goes to 0 right at the origin. So you have to put this in. And I've thought about different ways I could present that on the board. I think you just have to sit there and think about that one. Okay? But if you sit there and the code's there so you can play with it, okay? And I tried to plot a bunch of different things. But I've forgotten. Oh, that's, I just scrolled up too much. No. Oh, here it is. Okay, sorry. So there's the cubic, and if you were to run that again, you can plot what v is. It's screwing up. Why is this scrolling working weird? Okay, so v is my x squared. Okay. V dot of x gets this weird extra thing in there. Okay. V dot of x looks like this. It is negative inside the region I care about, but it's positive outside. So if I just asked for v dot to be negative, that wouldn't work. What I'm going to ask now is, for all places where v dot is positive, it better be outside my region. And the only reason that's a bad idea is because it hits 0 right there. So what I do is I just multiply in by this little x squared to make everything happy. And it takes out this little itty bitty thing, okay, and I guess that's the wrong one to plot. And it makes everything happy. So now this goes away from the origin enough that this thing is only negative when it's outside the region. Okay? And please do play with it. Okay, we have this tool now. All the questions we talked about, all the richness of like robust stability. Remember we talked about uncertain systems? I could find a common Lyapunov function that proves something about for all x and maybe for all parameters. Right? I could do that for this system. In fact, I've even got some pictures of that here. What if I just had a coefficient on top of this that was uncertain, right? So I have a gain uncertainty here, and delta comes from some domain. Then what would I like to do? I'd like that certificate to hold for all delta in that region and for all x in that region. And if I can push out and find the region of attraction, then I can say something, right? So first, what does that gain uncertainty look like? If I just plot various values of delta, I get those different curves. If I ask it for the region of attraction, it now finds this, right? Which is the true region of attraction. It's tight on the inside of that. Okay? If you have additive uncertainty, that's a different beast. What does additive uncertainty do to the function? It pushes it up and down. Right? Where's the fixed point on that one? It's a function of the parameters. If you ask for global stability, a Lyapunov function that's negative everywhere going to the origin, it will say no, as it should. But you can find an invariant set. You can ask for v to be less than or equal to 0. Okay? And find that biggest invariant set. And that's a meaningful computation too, right? If I want to know my quadrotor is going to, if my quadrotor is getting buffeted by the wind, the fixed point will move. It'll be at a different angle depending on what it's doing to the wind, but you'd like it to stay inside some region. Okay, here's one of my favorite region of attraction problems. Okay, you remember the van der Pol oscillator? It was one of the phase portraits we drew early. It's this nice vector field that oscillates, right? So if I simulate the system, that all trajectories go up to that limit cycle. It happens to be a polynomial system. So all of this polynomial talk we've been doing works. But what's the region of attraction question? It's kind of a hard question, right? So it's not converging to a fixed point, it's converging to a limit cycle. It's actually globally stable to that limit cycle except for the point of measure 0. So that's actually not the system that we think about. The system that we use as a region of attraction example is the time-reversed van der Pol oscillator. Take the same equations, put a negative sign in front of it, and that's like running the van der Pol oscillator backwards in time. And what does that do? Now the system, all those arrows change direction. Effective, well, not quite, right? But it runs backwards in time because the fixed point in the middle is now a stable fixed point, and its region of attraction is exactly where the old limit cycle used to be. Trajectories that started outside that will diverge to infinity. Trajectories that started inside that will go to the fixed point. So it's not only a polynomial system, it's a polynomial system with a goofy shape region of attraction that I know how to find. All right, so it's a favorite. And it turns out that if you search for Lyapunov functions for this system, then you get things like that. Okay, that one is actually a fourth order Lyapunov function. It's not an ellipse. It's not, the sublevel set of that is not an ellipse. So you know it's more than a quadratic. So I parameterized v to have coefficients up to x to the fourth. Since I'm searching for v, those coefficients, and the region, I have to do bilinear alternations. It starts off in the middle and goes ding, 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 and gets bigger, okay? There's a little extra trick that is how do you write an objective function which pushes out on the region of attraction? But that's a detail that the solver that you don't have to really worry about. Okay, you just call region of attraction; it should do the work for you. Sorry, Wei. Okay, so that's like a great example, I think. And although this sublevel set happened to be convex, I have other plots that look like this where the thing that sums of squares is able to prove is even a non-convex set. Okay? Now, here's the last point for today. And it's going to take you into your problem set. So, everything we've been talking about is about polynomials. And before that, with the nonlinearities we've been thinking about are not polynomial, they're like sines and cosines, they're trigonometrics, right? So it turns out, there's a natural question, is this stuff going to work for sines and cosines? It does, with a few tricks. First off, if you're given a general nonlinear system, you can Taylor expand it to get a polynomial approximation, and that actually works pretty well. But for sines and cosines, there's a special answer. In fact, rigid body dynamics are polynomial. Maybe I even have a slide like that saying that here. Sorry, wait. They are polynomial, and the trick is you change coordinates, okay? Take your sine theta away and write s, and make that an indeterminate. Take your cosine away, write c, okay? And then add this constraint s squared plus c squared equals 1. Now, if you have a general trigonometric function, you can't necessarily do that. But rigid body mechanics are not general. You never have cosine of like something else plus theta. It only ever appears as cosine theta, sine theta. And that's geometric. I mean, that's just the fact that these things are rigid body constraints. It's not there's a physical justification for that. These things live in a place that in the Cartesian space is a convex set, is a polynomial set. It's described by the sine and cosine. You never even get cosine of L theta or anything like that. You get sines and cosines, they enter in a very specific way in rigid body mechanics, okay? And therefore this substitution is fine. So you can write an optimization problem which uses the S procedure in the same kind of way to add the constraint s squared plus c squared equals 1. Let me do it. So I make my variables s, c, and theta dot are my indeterminants. Okay? I combine those into x. I write my pendulum dynamics, f. It's now got 3 variables. It's a little weird, but it's all good. And then I'm going to add a constraint that v is positive, that v dot is negative, but with this extra term with a Lagrange multiplier saying that sine squared plus cosine squared equals 1. Okay? Remember we said that p of x plus lambda of x, g of x is sauce, lambda x is sauce. That's for the case where you want g of x to be less than or equal to 0. If you have g of x equal to 0, if you have an equality constraint, it's exactly the same trick. You just don't have to enforce this. When g of x equals 0, this term contributes nothing So this must still be sums of squares. It must still be positive. Whenever g of x is not 0, you can multiply it by whatever you want in order to help this thing become positive. Okay, so it's almost exactly the same thing. I just don't have this extra constraint on the Lagrange multiplier. Okay, in all these cases, I add a little bit of scaling to help it out. I set my v 0 equals 0. I set some scaling for v. I call my solver, and guess what? This is what comes out. It's almost identical to mechanical energy. See the dashed lines hiding behind there? Right, especially with my scaling, I've made it, that's the reason I chose MGL, that's my scaling, okay? It's almost identical to mechanical energy. It's just shifted a little bit because it doesn't need Lassalle's invariance principle to prove stability. So this, using just polynomial optimization, gave me a global Lyapunov function for the pendulum, which proves the stability of all those fixed points, right? This one is actually 0, 0, 0, right? It's true for all x, and it came out of optimization. Cool, all right. See you next time.